Hello everyone, it's me, Professor Aaron Albert, here again with lesson 38. Let's learn some econ. So today we're just going to wrap up our probability uncertainty lesson, focusing on insurance values and their costs. And this is a particularly momentous video because it's the last one! We did it! We got through all the lessons! Hopefully it feels as much of an accomplishment for you as it does for me. So today's topic is insurance. We could talk about two different ways for one to be insured. Either we could have fair insurance, where you just pay what the insurance is quite literally worth, or we could have what I'll call actual insurance, or unfair insurance, or competitive insurance. And this is when an insurer will charge you money such that they extract as much from you as possible. So let's break it down such that we can see how these two differ. So fair insurance totally eliminates risk, step one, and it does it at cost, step two. So the way we do this is we charge insurance such that the expected value of the insurance is zero. That is, let's say that your car is worth 10 grand and there's a 50-50 chance that you crash it on base. That means you pay 5 grand, and if you crash your car, which you do half the times, they give you 10 grand, and if you don't crash your car, they give you nothing. So at the end of the day, the expected value of this situation is 5 grand beforehand. The fair insurance makes it such that you just have 5 grand either way. It completely eliminates the risk. Importantly, if people are offered fair insurance, they will fully insure every time. Importantly, however, insurance companies don't offer fair insurance. They have to run a business, they got to make money. So for this reason, people usually don't fully insure. The other way we can easily model insurance is talk about how an insurance company could maximally gouge you through what we'll call actual insurance. In this, they're going to charge you enough such that you are indifferent between being insured versus not. I.e., imagine you have a cost, and there's some, imagine you have a house, and there's some percent chance that your house burns down. They'll pay you the value of your house if your house burns down. So with the insurance, you can guarantee that you have a house, but you've paid some cost of insurance. They're going to make it so that your utility of having a house minus whatever insurance costs is exactly the same expected utility you'd get if you were uninsured. In order to see how this relates to all the things we've been mathing out, let's go to an example. This silly example involves rolling a die. So imagine you have a friend who owes you $5. That is, you are entitled to $5. You then, since you're a crafty, funny person, you tell your friend that if they roll a d6, if they get 1 through 5, you'll completely forgive their debt. They owe you nothing. However, if they roll a 6, they owe you $36. We're also going to assume that your utility of wealth is square root wealth. That is, your utility is W wealth to the half. And note that before this die spins, there's two possible states. Either you roll a 6, or they didn't roll a 6. So given these two states, what is your wealth in each scenario? Then, using that, what is your expected wealth? And then 3, what happens if you fully insure? Try it out. Let's see how you do. All right, well, note that if the die gets a 6, you have $36. That happens 1/6 of the time. If it gets a 1 through 5, the debt's forgiven and you have $0. Turning that into expected wealth, you'll have 0 times 5/6 of the time, plus 36 times 1/6 of the time. Looks like your expected wealth of this gamble is 6. Therefore, you actually are coming out ahead. He owed you $5, and they're going to give you, on average, $6. Lastly, what happens if we are able to then fully insure? Well, if we fully insure, we would just guarantee ourselves $6 in the end in each state. That is, if they rolled 1 through 5, the insurance company will pay you $36, and then you pay your insurance premium of $30. If they roll a 6, You have $36, so the insurance company pays you nothing. You then pay $30, and you end up with $6. And you'll note that this is completely fair, right? Hence, fair insurance. You pay $30, you get $6. The expected value of this was $6. You'll end up with the expected value of this no matter what. All right. Next, I already talked about how much fair insurance would cost. You pay $30. That is the expected value of your risk. That is, you lose 5/6 of the time. 5/6 of 36 is $30. Last question is, how much could the insurance company charge you, i.e., what would you pay to fully insure? See if you can figure this one out. In order to figure this out, remember, what is your utility if you've insured yourself? What's your utility otherwise? And how much money can they charge to make those two indifferent? So if you don't insure, your utility is 1/6 chance of getting the $36. So you have 1/6 of the square root of 36 plus 5/6 times square root of 0, which is just 0. So your utility is 1/6 the square root of 36, i.e. your utility is 1. That means they can guarantee you some amount of money such that your utility of that amount is 1. So we need to set square root of 36 minus x equal to 1. If we do this, we'll note that x should equal 35. So what this means is the insurance company will guarantee you $36, either you win or you lose, and then charge you $35 if you've indeed won, and the net effect is you'll have $1 in either state. Again, if they charge you $35, you end up with $1 in either state. Having $1 in your state has the same utility as what you'd get if you weren't insured in the first place. So that's how we calculate fair insurance values as well as what I'll call competitive or actual insurance values. One last silly thing we can do if we're used to playing with probabilities is think about what happens if we play a game known as the St. Petersburg Paradox, or the St. Petersburg Lottery. How this works is imagine that you flip a coin. If the coin comes up tails, you get $0 and the game ends. However, if the coin comes up heads, the game continues. You then flip a coin again, and if you get tails, you get $1. However, if you get a head, well, then you flip a coin again. And you can see how this works. Basically, you're going to flip a coin until you get tails, and then you get 1 to the x, where x is how many heads you've seen in the meantime. Sorry, you get 1 times 2 to the, So the question we have for you is, let's say you flip a coin, tails $1, heads flip again, and you have these exploding payoffs, right, where you get either 0 or 1 or 2 or 4 or 8. How much would you pay to play this game? If I said, hey, do you want to play the St. Petersburg Lottery? In your heart, how much would you say you'd be willing to pay in order to play this? Moreover, what do you think the actual expected value of this game ends up being? The answer may surprise you. Well, half the time you get $0, and then half the time the game continues. Half of that half, you get $1. So that means you get 1 a quarter of the time. But then the other half, it continues. Well, then half of that time, you get $2. So you get $2 an eighth of the time. But then the other half, it continues. Well, then half of that eighth, you get $4. But then the other half, it continues. This becomes a sequence of 0 plus a quarter, plus a quarter, plus a quarter. And in fact, you have infinite quarters together. So what is the value of this game? Should be apparent this game tends towards infinity, which is a little weird, right? We were doing what I thought was a normal thing, and it ended up being a non-convergent series. This is why it's called the St. Petersburg Paradox. It's quite surprising because this game, when it's described to you, doesn't sound very silly, but the results are incredibly silly, because I don't think the average person would pay infinite dollars to play this game. So in order to get out of the paradox, namely no one on Earth would pay infinite dollars to play this game, there's a couple of outs. And these results I'm going to credit partly to Wikipedia. First thing we could do is talk about diminishing returns, i.e. diminishing utility of wealth. If we don't value our wealth linearly, it's pretty natural that we don't put extraordinarily high values on the very rare but very high wealth states. The other thing we can do is talk about limiting the max payout. This game only has unbounded, i.e. infinite values, if the max payout is unbounded. If you stop this sequence at some value that is smaller than infinity, the game stops, right? You don't have infinite quarters, you have quarters that end after some period. So let's go through how these two caveats get us out of the St. Petersburg paradox. First of all, let's talk about diminishing returns. We saw that this game equals a half 0 plus quarter 1 plus eighth 2 plus 16th 4 plus blah, blah, blah. But imagine you have utility of wealth that's diminishing. That is, you value your first $1 million more than you value your second $1 million, more than you value your third $1 million. Which is pretty reasonable, right? Like, when I retire, when I'm older, I hope that I have some money, right? I'd be really sad if I have none. But if I have a ton of money when I retire, that ton of extra money is going to give me less utility than the money I need to pay my bills. The cliche diminishing utility function will be square root, so let's just square root it. So what is our utility for this game if we don't instead look at the value, we look at the expected utilities? Well, we'd have half of square root 0 plus half of square root 1 plus half of square root 2 plus half of square root 4. This is a convergent series. These get smaller, so we don't have an infinite sum anymore. Thank goodness. The other thing we could do is think about what happens if the game ends at x. And given the parameters I've set, I haven't actually found the precise values, but based on a tree I found on the Wikipedia, they said if you play a friendly game of this format with $100 max bankroll, it's worth $3. And if you play this game against someone whose max payout is $54.3 trillion, the actual value is $23. So although mathematically this game has infinite value, one, we don't value extraordinarily high values of money as much as we value small values of money, i.e. there's decreasing returns to wealth. And two, it's only going to have infinite value if we give the possibility for there to be infinite payoffs, and there's not. Anybody you play this game against is not going to have $54.3 trillion to pay you under the incredibly unlikely scenario that you just keep rolling heads all day. Just the best coin flipper on the face of the planet. And that's it. That's all the material we got. So I guess I just wanted to say, as I always do on the last lesson, thanks a bunch for learning all the stuff. My exact quote is thanks for your patience and diligence. And I would say that if you feel that you have a good grasp of all the material covered, that you should feel really proud of yourself, because I think we've covered all of the microeconomics that anybody in undergraduate could be expected to learn. So I guess don't forget to mash that like and subscribe button. Fire up Raid Shadow Legends, our unofficial sponsor. Other than that, thanks so much. See you next time.